SwayamPrabha. Digital India. Educated India.
This is the module on properties, and so let us continue discussing properties. We have already looked into the introduction of concept of a pure substance. We have discussed the phase change processes, and today we are going to illustrate some processes of phase change processes in the form of property diagrams. And apparently this becomes very useful diagrams to understand the phase change processes. There are many such property diagrams which you can illustrate in using temperature specific volume, pressure specific volume, and pressure temperature diagrams for the case of pure substances. So we are going to just take example of pure substances. Okay, so how does it look, the TV diagram for example? So I can draw it here. So this is your temperature and this is your specific volume. Okay, this is how it's going to look like for a pure substance. This here is a critical point. Now the volume, the lower side one is going to be a saturated liquid. So this line is saturated liquid and this one is going to be a saturated vapor, and the intermediate region is going to be saturated liquid vapor region. Okay, this region is going to be a compressed liquid and this is going to be superheated vapor. Okay, so this is a basic phase diagram for the pure substance. Now you can consider a simple piston such that the piston mass is fixed and you provide heat to the fluid containing in the cylinder. So this could be an example. Okay, and then you are providing some heat here. So in such case the temperature is going to rise for the case of system. So we can consider this operation in terms of phase change. So let us say we started with a compressed liquid and we have already illustrated this example in the previous lecture. So this is the case for the continuous increase in the temperature as we provide heat but the pressure remains constant, and until the point it reaches saturated liquid line, it remains a compressed liquid, and here at this point it starts vaporizing until we reach saturated vapor line, and then until this point the temperature remains constant. So this is where the temperature remains constant, so T is constant. Okay, and for a given P. Okay, and then once it reaches saturated vapor and after the last drop of liquid gets converted to vapor, it further now completely the system is vaporized. So you have a vapor, now the vapor temperature starts increasing. Okay, so then it essentially takes this path. So this is the case where some P is, let us say, P1. Okay, you can do this operation by changing the pressure of your system at a higher pressure, let us say. So this will be the case of P2 such that P2 is greater than P1. So this is a simple phase change process. Now you notice that the slope of this line, okay, is positive. So essentially del T by del V at constant P is greater than or equal to 0, right, because the intermediate range is 0. So here at this point, at any intermediate point, you have a system which consists of some vapor and some liquid. You can understand the same thing for if you change TV to pressure volume diagram. Let me just point one more thing before going to the next slide, that for a given pressure until it reaches the saturated liquid, it starts changing the phase. So this temperature which remains constant would be is saturated temperature at specific pressure. For example, in this case this is P1 because we have already mentioned P1 here, and in this case this would be Tsat at P2. So let us go to the next where we will going to change the pressure by keeping the temperature constant, and in this case we are going to draw a PV diagram here. Okay. So again here, so the lower volume range would be saturated liquid. So this is saturated liquid, this is saturated vapor, this is again critical point, okay, and this is the saturated, this region is going to be saturated liquid vapor region. This is your compressed liquid, this is a superheated vapor. So in this case what we are going to do, as illustrated in this figure, that you maintain the temperature by providing heat. However, the pressure, you started with a very compressed liquid, so that means somewhere you are here, and then you are decreasing the pressure by keeping the temperature constant. So this is how it's going to be, you are decreasing the pressure in this form, keeping the temperature constant. This happens until, so you go continuously drop in the pressure until you reach the saturated liquid line, and here again the phase changes to vapor, and further the pressure will drop as it crosses the saturated vapor line. Again this is a saturated vapor, right, and this is going to be saturated liquid. So this is about to vaporize, this is about to condense, these points represent in that form. So this is at certain temperature, this is at, let us say, T1. You can do the same operation at a higher temperature, and this is going to be T2. T2 is going to be greater than T1. Now note the slope here. The slope in this case is negative. So that means del P by del V at constant temperature is less than or equal to 0. So this is the case of PV diagram for the case of pure substance. Okay. Now we are aware of the fact that a state of a simple compressible fluid is represented by two intensive variables like temperature and pressure, right? And so any mathematical function which you represent in terms of two variables can be represented by a surface. So thus PVT surface of a substance would be more complicated diagram as shown in this case. So pressure, volume, temperature, and here for example you can clearly see there are many regions are there. There is solid liquid region, there is a vapor liquid region, the same thing which we have illustrated in PV diagram or TV diagram. You can take orthogonal projection and you can obtain this P temperature diagram as in the case of this. Okay, so this is your PT diagram. Okay, and so what you see here is, for example, the vapor liquid line here in this region, there could be many vapor liquid line, and each of them would point as would represented by a simple point here in PT diagram. And so we know that vapor liquid region is the case where your system consists of some part in vapor and some part in liquid. And similarly you have other case where is a triple line where you have three phases at coexistence. So that would be the case for your vapor, liquid and solid. Okay, they can change their volume percentage or the composition, okay, that and based on that you can have different volume here, and thus when you take a projection it's just a one single point here. So because there is only one line here. Okay, on the other hand you have a region of a vapor liquid, and that's why it acts here as a complete line. So this line would be vaporization line, and we will talk about this in the subsequent part of this lecture. Okay, so this is a orthogonal projection, and for the case of substance which expands, what you see is this negative slope of pressure and temperature, this region, particularly for solid. Because it expands on freezing. So this is something like, example it would be water. And this is another projection which is a PV diagram where you do see liquid vapor region, as we have already seen for our case in TV and PV diagram, and as well as this solid vapor region if it is a solid case, and then you have a triple line. okay, where the three phases coexist. So, but this is very complicated, particularly when you look into the PVT surface, and thus many times or usually we don't go for three-dimensional diagrams, or rather we prefer two-dimensional diagrams. You can also use the same thing for substances which contracts on freezing, which is more easily you can understand from the PET diagram, where the slope here for the case of solid liquid coexistence line is positive. So, let us look at now only the two-dimensional plots such as PV diagram. So, earlier we mentioned that, well, you have a PV diagram in this form, okay, and I drew in this kind of phase diagram. So, this was always vapor plus liquid, this was saturated vapor, this was saturated liquid, right. So, this is the same plot. When you include the solid phase on as well as the solid liquid, then essentially you get this kind of region. Similar to liquid vapor region, you have solid liquid region, and then the solid region is at lower volume up till higher pressure, okay. And then you have another region which is solid plus vapor, that means this is the region where solid and vapor coexist. And then you have this triple line, okay, triple line, which means the three phases solid, vapor and liquid coexist in this of different volume. So, volume can change. So, this is the case where you have a substance which contracts, which is usually this fluid system, and this is the case where you have a different slope for the case of substance expand, but now we have also included the solid vapor regions, okay. Okay, so now we are going to understand for the case of same phase transition for the case of a PT diagram. It is much easier compared to other cases. So, here you see these different lines are there. This is a pressure, again the temperature, pressure temperature plot, and this is your sublimation, this is your melting or fusion line. This is the case where for the substance that contracts on freezing, okay. So, and this is the case where it expands on freezing, such as water, okay. Now, this is your negative slope, so that means your del P by del T is negative, and this is your positive slope. And these are the different line, these are the line which represent coexistence. So, this line, each point here represent that you have a system containing vapor and liquid, and at this point you cannot distinguish vapor and liquid. So, you cannot do that, because here there is a homogeneous system. It is difficult to distinguish, and this is the region which this is here is a supercritical, and we will talk about supercritical fluid later in this course. Okay, so this is a vaporization line, which means the vapor and liquid are at equilibrium. This is the sublimation line, which means solid and vapor are at equilibrium. This is your melting or fusion line, so fusion, which it means is a solid liquid at equilibrium. Now, you can see that how these two different cases, where the one is at substance which expands on freezing and other case is your substances which contract on freezing, they behave differently. For example, you can start with a case where you have started with, let us say, a solid phase, and then you can change the pressure keeping the temperature constant. The way it transition or the path of transition, the phase transition it undergoes is quite different. So, take an example. For example, here if you are taking a solid phase, okay, far in the left side, and you keep the temperature constant and you drop the pressure, you undergo solid to vapor transition. So, this is a solid to vapor transition. So, this would be true for both the cases, but now you take a case somewhere here. For the case of substances which expands, you have, because for the case of, let us say, water, this will be solid, this will be liquid. So, you undergo liquid to solid to vapor, okay. But for the other case, which is the case of contracts on freezing, so this would be your solid to vapor, okay. And if you go from here, then it will be completely different, because you are starting from liquid to vapor, okay. So, already we have gone through some of the examples. Now keeping the temperature constant, here this is an example of where you kept the pressure constant. So this is where you change from A to B, that means change from solid to liquid. In the case of transition from C to D, you undergo transition from solid then to the case where you pass through triple point, which means you have solid, liquid and vapor, and then finally to the vapor phase. Now in the case of E to F, you undergo from solid to liquid to vapor phase, okay. And then you have a state where you do not have any phase transition because it is a supercritical region. So there is continuous here, okay. So I already mentioned the sublimation part, which is illustrated in this particular picture. Okay, for the case of water, the triple point is given here as 0.01 degree Celsius and this kilopascal. Okay, so when you undergo phase transition, there is the energy change effectively is represented by latent heat. So this is the amount of energy absorbed or released during a phase change process. So you will have latent heat of fusion, you will have latent heat of vaporization. So in the case of solid liquid, in the case of vapor liquid, and then in the case of a solid vapor, you have latent heat of sublimation. Okay, and this magnitude of this latent heat depends on the temperature and pressure, because it depends on what kind of phase transition you are or the system is undergoing. So for example, at 1 atmosphere, the latent heat of fusion of water is 3 to 3.7 kilojoules per kg, and for the case of vaporization is much higher. So this is the case of water which boils at different temperature when it has a different pressure. For example, at normal conditions, so normal atmosphere, it boils at 100, but at high elevation the boiling temperature decreases, and hence you have difficulty in cooking to address by looking at latent heat and as well as the conditions of the boiling. Let's take some examples of the phase diagram. This is the example of CO2 phase diagram. So you have a pressure, again a temperature. Now in this case, what is interesting is, so this is in Kelvin. So what is interesting is this triple point. This is a triple point where the solid, vapor and liquid are at equilibrium. Triple point is much greater than the normal atmospheric pressure. So you know is 101 point something, which should be somewhere here, okay. So this triple point is much greater. So at normal condition, if you take the solid CO2 at room temperature, what happens? It immediately vaporizes. Why? Because you can see it is more stable at this condition, let us say 273. It immediately jumps from a low temperature to vaporize, and that is why it is called as a dry ice. And this is an illustration which you can see that it vaporizes, and you can clearly see the conversion from solid to vapor. Now there are many other phases which we see. It is not just a solid, liquid and vapor, but solids can have many different forms, and that is also referred as allotropes. So you are aware of different forms of carbon. You can put this in terms of phase diagram, and this is your P and temperature for carbon, and you can see this is of course your triple point, but then there are other points as well where different phases coexist. So triple point will be one for a system where vapor, liquid and solid coexist, but there could be other triple point where you can have two solids coexisting with liquid, or three particular solid phase at coexistence. Okay, so this is just an example of graphite, diamond and the carbon liquid at very high temperature for that matter. The other example would be your ice. So ice has various different forms, and which is represented into 1, 2, 3, 4 and so forth. It has a triple point 1, but it has many other triple point as well. So let me just pay a little more attention to this and explain here. This is more complex diagram, pressure and temperature. This is again your triple point, okay. So at normal condition, for the case of ice, what you see is something called hexagonal form of ice, okay. So that is close to, that is almost 0 degree Celsius at normal pressure. If you decrease the temperature to around 37, minus 37 degree Celsius, and it is argued and it is a debate that the ice, the water changes its structure from hexagonal form to something called cubic structure, okay. So let us look at it. What is hexagonal? Well, this is a simple hexagonal close packing where the water molecules fills up the positions represented here as A first as a first layer and B in the second layer. So that becomes AB kind of pattern, and that is what the ordinary ice which is IH form, and it what is you see those kind of structure in a snowflakes giving their 6-fold geometry. But another case which we call a cubic, the third layer, the first two layers are the same, but the third layer occupies this particular position here as shown in this particular picture, and thus the sequence becomes A B C A B C. Okay. Now apparently this is not, it's argued that this is not very stable, it does not stay for a long time. It's also argued that in normal conditions also you can see cubic phase, and hence it's quite a debate of discussion, or it's intense research area in this direction. Now if you further decrease the temperature from -37, it actually turns to something called 11 orthorhombic structure. Now this orthorhombic structure apparently is found in Antarctica ice, and it has an interesting property. It is called ferroelectric kind of properties, which essentially electrically polarized, just like for example a ferromagnet which spontaneously magnetize. So you can see that phase transition can interestingly change many different properties, and thus it's of quite interesting subject of research. Okay, so I will kind of wrap up this particular lecture by just looking at this property of ice, and it's called rigidation property. Well, this is a phenomena which is the case of melting under pressure and freezing again when the pressure is reduced. So essentially the water or the ice, for example, it has the property to expand upon freezing. Okay. For the case of melting, it compresses. So essentially this is an interesting material. Okay, for example, the melting point of ice falls by 0.0072 degrees Celsius for each additional atmosphere pressure applied. And this has been argued that since you apply pressure, you melt the ice, and by melting an ice you have a thin layer of fluid, and hence you can ice skate on it. But let us look at it whether this is feasible at all or not. Okay, but because as we see from the phase diagram that for a small change, for example, if you want to melt ice at -4 degrees Celsius, you need to apply 500 atmosphere pressure. Now let us look at it, how it is possible that you can ice skate. Okay, so this is again rigidation phenomena is nothing but a phenomena of melting under pressure. It occurs for the substances such as ice. Okay, so this is the zoomed pressure temperature diagram for the water case, and now you can take an example of an ice skate person. Let us say a typical weight of a skater would be 50 kg. The area of the skate blade could be 3 millimeter into multiplied by 200 millimeter. You can calculate the pressure due to the weight and apply it to the thin skate blade. The pressure comes out to be 8 atmosphere. And thus 8 atmosphere, is it suitable? I mean, is it sufficient to melt the ice to give you sufficient lubrication in order to reduce the friction, and you can ice skate? Now you can clearly see even if it is a minus, let us say 5 degree, okay, atmospheric condition, the amount of pressure you need, this is your solid, this is your liquid, okay, for the case of water, amount of pressure you need would be much more, many times. I mean, this should be more than 10, 20, or almost like maybe with respect to scale it could be something like 250 atmosphere. Okay. So certainly the applied pressure is much lower. So there is more complex phenomena going in this, and hence this is also a debate. So that will be the end of this lecture. Next we are going to study thermodynamic property from a property table. So we introduce the property table and we will discuss about that.